Hey, and welcome. Today, we're diving right into the heart of chemistry. I mean, the real secret sauce behind what makes a chemical reaction actually go. This stuff is fundamental. It governs everything from how your body gets energy to how fireworks light up the night sky.
I mean, really think about that for a second. You've got dynamite exploding in the blink of an eye, and then you've got an old nail slowly rusting away over years. Both are chemical reactions, right? So why the massive difference in speed? What's the hidden rulebook that the molecular world is playing by? Well, the answer is actually pretty cool.
You heard that right. The core idea, the secret to all of this, can be summed up with a simple analogy: a high five. And we're going to use this idea of a molecular high five to make sense of everything that has to happen for molecules to decide to react with each other. So, here's our game plan. We'll start with the basics of that molecular high five. Why molecules have to collide in the first place. Then we'll get into why not every high five works. After that, we'll talk about the energy barrier they have to clear, how we can cheat the system to speed things up, and finally, we'll look at the master equation that ties this whole thing together. Okay, so first things first, the most basic rule of all. Before anything can happen, our little reactant molecules have to actually find each other. I mean, you can't have a reaction with something on the other side of the room, and neither can a molecule. And that's pretty much the formal definition of collision theory. It's the foundation for everything we're going to talk about. Your atoms, your ions, your molecules, they have to physically slam into each other to have any chance of forming new bonds. No collision, no reaction. It's as simple as that. But, and this is a big but, here's where it gets way more interesting. Just bumping into each other isn't enough. Not even close. If it was, everything would just be reacting all the time, totally out of control. Nope, there are a couple more rules to this molecular high five. So here's the deal. There are 3 conditions that have to be met. First, the collision. Yeah, we got that. They gotta bump into each other. Second, they have to hit each other in just the right orientation. Think about a bad high five. When you go for the palm and you hit their elbow, it just doesn't work. It's the same for molecules. And third, they have to collide with enough energy. A lazy, floppy high five is just sad. You need some force behind it. Let's look at a real example. For carbon monoxide to become carbon dioxide, its carbon atom, the C, has to be the part that smacks into the oxygen molecule. If the other side, the oxygen end of the CO, hits it instead, nothing. They just bounce off each other like billiard balls. No reaction happens. The angle, the alignment, it's everything. So, what happens when it all goes perfectly? The collision happens, the angle is just right, and there's enough energy? Well, for a tiny fraction of a second, the molecules form this thing called an activated complex, or a transition state. This is it. This is the peak of the action. It's the moment the high five actually connects, where old bonds are stretching and breaking and new ones are just starting to form. It's super unstable, and it falls apart almost instantly to become the final products. All right, let's zoom in on that third rule, energy. Because for most reactions, this is the big one. This is the main hurdle. It's not enough to just show up. The colliding molecules have to bring enough kinetic energy to the party to actually get things started. And that minimum energy has a name: activation energy. You'll see it written as EA. Just think of it like the cost of admission to the reaction club. If the molecules that collide don't have enough energy to pay that price, they can't form that transition state, and they just get turned away at the door, bouncing off unchanged. A really great way to picture this is to imagine the reaction as a journey over a hill. The reactants, our starting molecules, are just chilling at the bottom of the hill, on one side. They're stable, they're fine, but they've got the potential to change into something new. The height of that hill, that is the activation energy. The molecules have to get a big running start from their collision to climb all the way to the top. And that peak, the very top of the hill, that's our transition state. Once they make it there, they can just roll down the other side and become the products. So you can see, a really big hill means a high activation energy, and that means a slow reaction, because very few molecules are going to have enough energy to make that climb. Okay, so if we know the rules of the game, you need a collision, the right orientation, and enough energy, how can we start to, bend those rules in our favor? How do we make reactions happen faster? Well, there are 2 main ways we can stock the deck. First up, we can just increase the concentration.
This one's pretty straightforward. If you cram more molecules into the same amount of space, they're just going to bump into each other way more often. It's like trying to navigate a super crowded room versus an empty one. You're just going to have more collisions. And more collisions per second means a higher chance that one of them will be a successful reaction-causing one. Second, and listen, this one is huge, we can increase the temperature. See, temperature is just a measure of how fast molecules are moving around, their average kinetic energy. So when you heat something up, you're making those molecules zip around faster and hit each other harder. What that means is at a higher temperature, a much, much larger fraction of those molecules will actually have enough energy to get over that activation energy hill. Now, of course, scientists love to describe the universe with math, right? And it turns out there's this one beautiful equation that wraps up all these ideas we've been talking about: the collision frequency, the orientation, the activation energy, all into one neat little package. And that package is called the Arrhenius equation. This is like the quantitative rulebook. It gives us a hard number, the rate constant, which we just call K, that tells us exactly how fast a reaction is. A big K is a fast reaction, a tiny k is a super slow one. And it connects that speed directly to the physical things we've been talking about. Okay, here it is. I know it might look a little intense with the letters and the E and all that, but trust me, the idea behind it is exactly what we've been discussing this whole time. On the left, K is just the reaction's speed, and everything on the right, well, that's what's controlling the speed. So let's break it down. That first part, A, is called the frequency factor. That's all about the high fives themselves, how often molecules are colliding and if they're in the right orientation. The second part, that E term, that's the magic. That part calculates the fraction of those high fives that are actually strong enough to work, the ones that have enough energy to beat the activation energy, EA. And look, temperature, T, is sitting right in the heart of that term. That shows you just how powerful it is in controlling the whole reaction. And get this is not just some theory. Look at this real-world data for the decomposition of hydrogen iodide. At 555 Kelvin, the rate constant K is tiny, like ridiculously small. It's a painfully slow reaction. But watch what happens when we crank the heat up to 781 Kelvin. It's not even double the temperature, but the reaction speed, that K value, it just explodes. It jumps by a factor of over 100,000. This is the key insight, you guys. Temperature doesn't just nudge a reaction along, it has this insane exponential power over its speed. And you know what the coolest part is? By measuring that rate at a couple of different temperatures, scientists can use the Arrhenius equation to work backwards and figure out that crucial number, the activation energy. For this reaction, that energy hill the molecules have to climb is 180 kilojoules for every mole. This equation literally gives us a window into the invisible energy landscape of a reaction. So let's just boil this all down. What do you absolutely need to remember? First, the 3 rules of the molecular high five. You gotta have a collision, it's gotta be in the right orientation, and it's gotta have enough energy. Second, that energy requirement is called the activation energy, and it's the main roadblock for almost every reaction. And finally, we know how to push reactions along, increase the concentration for more collisions, or jack up the temperature to make those collisions more powerful. But that leaves us with one last really interesting question. We know how to play the game by cranking up the heat or cramming more stuff in. But what if you could cheat? What if there was a way to actually lower the activation energy hill itself, to basically build a tunnel through the mountain for the reaction? Well, there is, and that's a story for another time. Thanks for joining me.